Hi everyone, my name is Peiyu, a PhD student from the University of Western Australia. It's my honor to talk about our recent work, local path integration for attribution. And nowadays, deep learning has received great success in many real-world applications. However, current deep models lack interpretability for their prediction. For example, deep models are shown to be vulnerable to the human imperceptible noise generated by some adversarial attacks. And therefore, how to explain the prediction made by the deep model has received much attention. Attribution methods are such popular tool to interpret the model prediction for an input. For a given prediction, an attribution method aims to assign the importance score to each input feature. And the following figure shows some popular attribution methods. Among different attribution methods, integrated gradients are one of the most popular attribution methods. And motivated by the game theory, integrated gradients integrate input gradients from a reference input to an input along a linear path. Equation 1 formally defines integrated gradients, and the right figure shows the attribution map generated by the integrated gradients for the input image with a bubble bird. And in contrast with other attribution methods, integrated gradients enjoy important and desirable characteristics and axioms. For instance, integrated gradients satisfies completeness. The completeness requires the summation of attributions can recover the output change, and the right figure shows the example of completeness. The blue line shows the output change between the input and the reference. The cumulative gradients with the red line can approach the output change as the path from the reference to the input. And in addition, integrated gradients also satisfy the implementation invariance that requires the attributions to be identical for two functionally equivalent networks. Also, integrated gradients can guarantee desirable axioms. There are also some limitations of integrated gradients. Firstly, integrated gradients choose zero input as the reference, causing blindness to black color. For example, integrated gradients cannot correctly assign the attribution for the black part of the input image. And generally, path-based attribution methods are blind to specific colors due to the unreliable reference choice. To solve the blindness problem in integrated gradients, many attribution methods with multiple references are proposed, including uniform noise, Gaussian noise, or max distance input references. However, this reference is still far away from defining the feature absence, and reference sample is easily out of the learned distribution, causing incorrectly attribution integration. And secondly, integrated gradients are proven not to satisfy the weak dependence axiom. Given a piecewise linear model, weak dependence axiom requires that attributions should weakly depend on the input and only depend on the model parameter. The intuition behind the weak dependence is that attribution methods should faithfully reflect the model behavior instead of the input. And the following example shows that IG violating weak dependence results in a counterintuitive attribution. Given two pairs of points x1 and x2 equal to 1.5 and 0.5 and 4, that all satisfy x1 and x2 larger than 1. The attribution of the two pairs of points are expected to be 3 to 1. However, integrated gradients result in 2.5, 3.5, and 10, and 6. The results show that attribution generated by IG depends on the choice of the input and thus violates the weak dependence axiom. And to solve the drawback, Fuggrant considers bias gradients in the attribution calculation process. However, Fuggrant is shown easily to be perturbed by small noise. To address the two limitations, we propose our local path integration. And firstly, motivated by the expected gradients, we also take the learned underlying distribution as our reference, and which enables the reference within the learned distribution. And instead of finding the feature absence, our method compares the relative importance with the learned features as the attribution. And secondly, we consider the weak dependence in the path attribution method. Based on the definition of weak dependence axiom, in a symmetric function, the lemma 1 shows that if we choose the underlying distribution of the neighborhood of input as the reference, the attribution method can satisfy the weak dependence axiom. As such, we can obtain the intuitive results in this example. Given the two pairs of points, the IG variant can calculate intuitive results. For example, IG variant results in the attribution 3 to 1. Then we provide an overview of our proposed local path integration. Integrated gradients select a zero input as the reference, which makes the integrated gradients underestimate the importance of darker pixels in the input. And expected gradients uses random points on the learned distribution, which cause expected gradients to estimate the background part. And by contrast, our proposed local path integration identifies local distribution of the input point and integrates gradients from the local region. Therefore, our method can consistently calculate accurate attribution. To achieve this goal, we propose a strategy to identify the local underlying distribution and sample references from the local distribution. Inspired by the Activation Atlas, we first scan all the training examples and obtain the output logics. And since the deep model is trained under independent and identically distributed assumption, and the logic output can be viewed as the unnormalized log densities of data distribution, we collect all output logics to represent the discrete distribution. And for the sake of understanding, we employ UMath to project the high-dimensional logic output into 2 dimensions. And as such, we can draw the learned distribution of the model by collecting all output logics. And considering that deep models has converted the image from the irregular input space to regular class space, and we employ k-means with oscillating distance to divide the overall distribution into different local regions. And therefore, the learned distribution is further divided into different neighborhoods by clustering. And in this part, we collect each clustering center to locate the region of each subdistribution. And at last, each subdistribution is further clustered to find the representative images for drawing the subdistribution efficiently. And specifically, we collect the image closest to the cluster center as the reference. And in this way, we can sample the reference for representing the local distribution. After identifying the local neighborhoods of overall learner distribution, the pipeline of the local path integration is given as follows. Given an input image, our method first obtains its output logics. And secondly, we can index the subdistribution by comparing the distance between the output logic and the clustering centers. And then we can index a set of representative images as the references. And at last, the attribution can be calculated by integrating gradients based on the selected references. And then we can formally define our local path integration as shown in equation 5. And given the input image X and its corresponding neighborhood distribution Di, our local path integration integrates gradients along the path from input to the reference sampled from the distribution Di. And to efficiently estimate the integration defined in equation 5, we employ Monte Carlo estimation to redefine the local path integration with an expectation form for efficient attribution estimation, as shown in the equation 6. Next, we conduct extensive experiments to evaluate the reliability of our proposed method. Firstly, we introduce some popular quantitative metrics and our proposed metric for attribution methods. Insertion and deletion games are 2 popular metrics for attribution methods. Since a reliable attribution method should assign higher importance score to features which plays a key role in predicting a certain class. As a result, removing these pixels should cause a higher output change. Insertion and deletion games evaluate the output change on the most and least important features. However, removing pixels from the input image will cause input distribution shift. Therefore, it is unclear whether the performance variation comes from the input shift or removing the informative features. To mitigate the distribution shift problem, other metrics remove the most or least important pixels and retrain the model to test the output change. However, retraining models is expensive and time-consuming, which may also cause model parameter change. And since the main target of an attribution method is to explain the given model, retraining model is also not a faithful evaluation metric. And to balance the efficiency and distribution shift, we propose a method called differ-ID that measures model performance change difference between the insertion and deletion games. Differ-ID is more comprehensive than the insertion and deletion game alone. And in addition, since the shift occurs during both pixel insertion and deletion, focusing on their relative difference instead of their absolute values helps neutralize the effects of distribution shift. We first evaluate the reliability of our method on the proposed differ-ID. The four figures shows the fractional output change and the accuracy change under different percentage deleted and inserted pixels on both WGG16 and ResNet34 models. And the table 1 also reports the area under curve values for our local path integration and other attribution methods on both WGG16 and ResNet34 models. And we can observe that our method can also outperform other popular attribution methods on both insertion and deletion games. And this quantitative results show that the proposed local path integration is able to consistently outperform all the related methods. Then we also test our method on AAAI and differ-AAAI benchmarks. For different attribution methods, we retrain the pre-act ResNet on both CFR10 and CFR100 datasets. And we can observe that our local path integration method can generally outperform other attribution methods on both benchmarks and datasets. In addition to the overall comparison, we also evaluate the effect of different key hyperparameters. Since the performance of path attribution methods rely on the number of references, the following figure shows the fractional output change under different numbers of gradients computations of references. And we can observe that our method can efficiently achieve a higher performance in comparison with other methods. And besides, we also test the effect of the neighborhood number. And we can observe that different numbers of neighborhoods can affect the reliability. And it should be noted that our method can also outperform expected gradients when using the entire distribution, and which demonstrates that our method can better estimate the underlying distribution. Additionally, we also test the number of interpolation points. In the first figure, we test the area under curve value of the differ-ID as the number of interpolation points grows. And we propose a technique to efficiently estimate a distribution by clustering, so we employ the density of each cluster as the density function. Then we test the effectiveness of the proposed strategy for estimating the probability function. And the second figure shows the performance of local path integration with clustering density can outperform the random density, and which also shows our method can better estimate the underlying distribution. And in the third figure, we evaluate the computation time for 10,000 images sampled from ImageNet validation dataset over different numbers of backpropagations. And the results show that the efficiency of local path integration can approach the integrated gradient. And the expected gradient has a high memory overhead as it needs to load the larger training dataset to sample the reference. Hence, it has the worst efficiency among the solutions. And the adversarial gradient integration has similar efficiency as the local path integration when based on one targeted adversarial classes. The results shows that our method can achieve outstanding trade-off between reliability and computational overhead. Then there are some visualization comparison between our method and other attribution methods. In conclusion, to elevate the violation of the weak dependence property, we propose strategies to identify the local neighborhood of the learned distribution. And then we introduce a local path integration that focuses on the local neighborhood of an input to select the reference used to integrate the model gradients. And then we contribute a comprehensive metric, and at last our extensive results and comparison with other path attribution methods establish the efficacy of our technique. There are some major references for our work, and thank you for listening.